previous unit, we've looked at a few different kinds of rates. The rate of change of position, which is called your velocity, the rate of change of velocity, which is called your acceleration, how fast a population is growing. In this lesson, we're going to introduce the idea of related rates. The fact that how fast one thing is changing affects how fast a different thing is changing. And in this lesson, we're just gonna introduce this idea and look at how to set up problems, and then in the next lesson, you're going to learn how to actually solve these problems. So, introduction to related rates. Many variables have a familiar relationship. In other words, a way variables are related to each other. And a great example of this is the Pythagorean theorem. If you know you have a right triangle with sides A, B, and C, where C is the hypotenuse, you know that these sides are related by a squared plus b squared equals c squared. So what would happen if we started to change the length of each of these sides? Say we change them in time. So here I've got a right triangle, let's say ABC. If I start to change the length of one of my sides, I'm also changing the hypotenuse, and the rate of change, how fast the side is changing, will also affect how fast the hypotenuse changes. So by grabbing this green dot here, I'm only really affecting the length of this bottom side, but by doing that, by changing the length of the bottom side, I change the length of the hypotenuse. And similarly, if I change the length of the height of my triangle, I'm also changing the length of the hypotenuse, even though one of the sides isn't changing. And I can change them all at once as well, and they all are interrelated. But while they are changing, they will maintain that Pythagorean theorem that we're so familiar with, a squared plus b squared equals c squared, no matter what. And because they maintain that relationship, because I'm maintaining a right triangle, the relates end up being related. Similar example would be the volume of a cylinder. So I know my equation for volume equals pi r squared h. So if, for whatever reason, I decided to change the height of my cylinder, my volume would change as well at the same time. So here I've got a cylinder. If I change that height, the volume of my cylinder changes. Height gets bigger, volume gets bigger, height gets smaller, volume gets smaller. And so that rate of change of height maintains that volume relationship and also changes the volume of the cylinder. Same thing if I was going to change the radius of my cylinder. Without changing the height, I could change the volume. And the rate that my radius is changing will affect the rate that my volume changes. And I could do both at the same time if I want, and they will maintain that volume relationship. So these are what we call related rates. How fast one thing is changing affects how fast another thing is changing. So let's say a triangle's dimensions are changing. This means a dimension A, B, or C has a rate of change, and this rate is related to another dimension's rate of change. Now when we have these, we usually differentiate to find the rate of change. We differentiate the relationship with respect to one specific variable, and this is like implicit differentiation. Usually, but not always, this is respect to time. For example, if A is changing by increasing by 1 centimeter per second, how does that affect C? And again, we're thinking, okay, per second, so we want to differentiate with respect to time. So we want to go d by dt is what we're trying to find, d by dt of this whole relationship, assuming that A, B, and C are also related to time. So when we do that, we're going to use the power rule to bring our 2 down in front. We've got our A, you can put the 1 up there, and then this is going to multiply by dA dt, depending on how fast A is changing with respect to time. Then we're going to add to that, again, power rule, we got then 2 times B times dB dt, and that would be equal to, again, power rule, 2 times C times dC dt. And then if we have numbers for each of these things, we know how fast they're changing, increasing, decreasing, have starting values for A, B, C, we can solve different problems. But in this lesson, we're just looking at how to set up the relationship and not necessarily how to solve it. Same idea with this volume. I could differentiate this with respect to time, and if both R and H are changing, that would require me to use the product rule. If just one of them is changing with respect to time and the other one is constant, then I wouldn't need the product rule. I could just use straight up power rule. So it really depends what we're looking at, what's changing, how it's all going to play out. So we're going to play around with this idea, mostly with the Pythagorean theorem in this lesson, and then you get to play around with it in the homework with a few other formulas. So let's see how this goes. One example, a police car is approaching a right-angled intersection from the north. So up here we got north, and is chasing a speeding car that has turned the corner and is now moving straight east. So the police car is going towards the intersection from the north, and the car is going away from the intersection to the east. We want to set up a relationship to find an equation that shows the related rates of the vehicles with respect to time. So again, when we set this up like this, we've got our right triangle, which is going to allow us to use the Pythagorean theorem. I'm going to call the side that's to the north y because it's along the y-axis, and the side that's along the x-axis towards the east, I'm going to call that x. And again, I can call this pretty much anything I want. I'm going to use c because it's my hypotenuse, but you could use z if you wanted. You could use m, you could use d, whatever. It doesn't really matter. We're just picking amounts. So we know that as the police car gets closer to the intersection, that would decrease the distance between the two cars, which is c. But as the car speeds away from the intersection, that's again going to increase the amount of the distance between them, which is c. So again, this is Pythagorean theorem. I've got x squared plus y squared equals c squared. Everything's moving, so these are all variables with respect to t. So I'm going to take the derivative again with respect to t. So this is going to be 2 times x dx dt plus 2 times y dy dt, and this is going to be then 2 times c dc dt. So again, assuming each of these things is moving with respect to time, this would be the velocity of the speeding car going east, this would be the velocity of the police car coming south, and this would be the velocity or the rate of change of how far apart they are as they move. Okay, so again, we're just going to set up the questions in this lesson, and then in the next lesson you'll see when you actually start plugging numbers in and solving. Sometimes we have an expression where some dimensions are constant. So I said with the volume formula, you might not be changing the height and the radius at the same time. You might just be changing one. So that has different implications depending on what our question is. So it says, an airplane at point A is flying on a horizontal path that will take it directly over an observer, point O. So again, think of this as the observer is standing, here's the ground, the observer's on the ground, and the airplane is flying so that it will go directly above the observer. So I'm going to actually connect those. And we want to relate the rate of change of the distance between the observer and the airplane. So that would be this distance, which is your hypotenuse. Let's see if I can draw a little bit of a straighter line. We want to relate that rate of change. Again, I'm going to call that c just for the sake of the fact that it's a hypotenuse. You can call distance between them. So we want to relate this distance between the observer and the airplane and the horizontal distance between the two. The horizontal distance I'm going to call x is this distance here. And we're told that, I'm going to call this y, we're told that this y is a constant altitude. So my original expression is going to be the same. This is going to be then x squared plus y squared equals c squared. And if I realized right away, because it's maintaining a constant altitude, this distance isn't changing, that means when I take the derivative of y, it's just going to actually disappear. Because this amount isn't changing, its velocity is 0. If I forgot that and I just did my regular, 2x dx dt plus 2y times dy dt equals 2c dc dt, then at this point I would go, hang on a second, we've got a constant altitude, so y is not changing with respect to time. That means this full quantity is going to be 0, which actually means this whole thing just disappears, and I'm left with then 2x dx dt is equal to 2c dc dt. In other words, there's a relationship, a direct relationship between how fast x is changing and how fast c is changing that is also related to how far apart they were to begin with. And I could clean this up by dividing them both by 2 if I wanted to, so I'd get x dx dt equals c dc dt. And again, in the next question, next lesson, you will be asked to solve different things to do with that. So that's it for this lesson. Again, most of our examples with the Pythagorean theorem, but we can also play around with other relationships and differentiate with respect to time. Good luck with your homework and your mastery quiz.